Okay, so picture this. You grab your phone, plug it in, it's the end of a long day, battery's flashing red, right? And boom, it starts charging. Magic. Well, not quite.
You hit the nail on the head. The magic is actually a tiny component directing the flow of that electricity, kind of like a one-way gatekeeper inside all our electronics.
We're talking about the PN junction diode, right?
Yeah.
And full disclosure, our sources today, AC circuits, capacitors, basic electronics, none of them have a big, bold chapter 20 dedicated to these diodes. But the thing
The
is,
thing is, those sources, they lay the groundwork. The core concepts are all there, kind of like the ingredients, you know? We just need to put them together to understand how this fundamental piece of tech actually works.
so that's our deep dive today, folks. We're going to demystify this little component, the PN junction diode, that's quietly doing its job in pretty much every modern gadget you can think of.
And we'll keep it clear, we'll keep it concise, no tech overload, promise.
Deal. So where do we start?
Let's get back to basics. Back to those building blocks, you know, the semiconductors.
Semiconductors. Okay, yeah, they're not quite conductors, right? Not like the copper wires we all know, where electrons just zip around freely.
Right. And they're not insulators either, those stubborn materials that just refuse to let electricity through.
So semiconductors, they're kind of in between, huh? Like picky about when they'll conduct electricity?
Exactly. They're that Goldilocks material.
Yeah.
Not too conductive, not too insulating, but just right.
And the key to their pickiness is valence electrons, right?
You got it. Those outermost electrons in an atom, they're the ones that can break free and carry that electric charge. And it all comes down to how many each atom has in its outermost shell.
So conductors, those eager beavers, they've got just one or two valence electrons ready to jump ship at any moment.
Then you have insulators, packed to the brim, full outer shells, holding those electrons tight, not letting them budge.
Okay, so semiconductors, they've got what, 4 valence electrons? That's pure silicon, right?
Pure silicon, yeah. Each silicon atom's got 4 valence electrons, and it wants to share those with 4 neighbors, you know, form these strong bonds like a tight-knit group, all holding hands. It's a stable structure called a crystal lattice.
So everyone's paired up, no one's free to roam around, no flow of electricity, right? Makes sense.
Now, here's the real magic trick. We got to get some of those electrons moving. We got to introduce some chaos into this perfectly ordered system. Enter doping.
Doping. Okay, yeah, that sounds kind of mischievous, like we're tampering with something.
It is cambering, but in a controlled, very clever way. It's all about intentionally adding impurities, just a tiny bit, to that pure silicon crystal atoms with a different number of valence electrons.
Okay, I'm intrigued. Let's talk N-type doping first. What's the secret sauce there?
For N-type, we sneak in an element like arsenic. Now, arsenic, it's got 5 valence electrons. So when it replaces a silicon atom in that crystal lattice, 4 of its electrons bond nicely with the silicon neighbors. But that 5th electron, it's like the odd one out.
The fifth wheel, huh?
Exactly. It becomes loosely bound, free to roam around within the material, becoming a charge carrier. And guess what? More charge carriers mean better conductivity.
So the N stands for negative because of these extra negatively charged electrons. Makes sense.
Precisely. Now let's flip the script. P-type doping. What do you think we do here?
I'm guessing instead of adding electrons, we take some away.
You got it. We introduce an element like indium, which only has 3 valence electrons.
Okay, so when indium tries to fit in with those silicon atoms, it can only form 3 bonds. That leaves a gap, right?
That's right. It leaves a hole, a missing electron. Now here's where it gets a little weird.
Yeah, weird sounds about right when we're talking about missing things conducting electricity.
It's counterintuitive, but bear with me. Think of it like a parking lot, right?
Mm-hmm.
If there's an empty spot, a car can move into it, leaving another empty space behind. So in p-type material, an electron from a nearby bond jumps into this hole.
So it's not the hole itself moving, it's the electrons shifting around, creating this illusion of movement.
Exactly. That hole, that absence of an electron, it acts like a positive charge. And as electrons keep jumping to fill it, it looks like the hole is moving. That's how current flows in p-type material. And P, you guessed it, stands for positive.
All right, so N-type has extra electrons, P-type has these moving holes. Now the million-dollar question, what happens when you put them together? This is where the PN junction diode comes into play, right?
This is where the magic happens. So we join an N-type and a P-type semiconductor. What do you think happens right at that junction?
Well, those free electrons in the N-type material, they're probably going to see those tempting empty holes in the P-type and...
You got it. They rush across the junction to recombine with the holes. It's like a love story, opposites attract.
Oh, matchmaking.
But there's a twist. This recombination creates a zone around the junction, depleted of both free electrons and holes.
So no more free love, huh? It's like a dead zone for conductivity.
That's exactly what it is. It's called the depletion region, or sometimes the barrier. And this barrier, my friend, is the heart of the diode's magic trick.
Okay, so we've got this barrier, this gatekeeper. But how do we control whether it lets electricity through or not?
That's where biasing comes in. Let's start with forward bias. Imagine we connect the positive terminal of a battery to the p-type side, called the anode, and the negative terminal to the n-type side, the cathode.
Positive to P, negative to N. Got it.
This applied voltage, it's like giving those electrons and holes a little push towards the junction. It shrinks that depletion region.
And when the depletion region gets thin enough?
Boom. Current flows. Once the applied voltage overcomes a small internal barrier, the junction voltage, which is usually around 0.7 volts for silicon diodes, electrons and holes can easily cross the junction and recombine, creating a current.
So forward bias is like opening the gate, letting the current flow.
In an ideal world, yes, a perfect diode would have zero resistance in forward bias. But in reality, we do have that junction voltage and a tiny bit of internal resistance. But the main point is, forward bias equals current flow.
Okay, now reverse bias. Time to flip the switch, right?
Exactly. We reverse the polarity of the battery. Positive terminal goes to the n-type, negative terminal to the p-type.
So now the battery's pulling the electrons and holes away from the junction.
Exactly. This widens the depletion region, making it an even stronger barrier to current flow.
So reverse bias slams the gate shut, no current allowed.
Pretty much. The diode offers really high resistance, blocking almost all the current. In an ideal diode, no current would flow at all. It'd be like a perfect insulator.
But you mentioned leakage current earlier. What's that about?
Yeah, that's the real-world wrinkle. Even in reverse bias, there are a very few, minority charge carriers. Holes in the n-type, electrons in the p-type, these guys can sneak through the depletion region, creating a tiny, usually negligible current.
Got it. So it's not a perfect off switch, but pretty darn close. This one-way current control, it seems like a pretty neat trick and a useful one, I'd bet.
You bet. This ability to conduct in only one direction is what makes the diode so incredibly useful. It's everywhere in electronics.
And one of its main gigs is in rectifier circuits, right? Something our sources on AC circuits definitely touched upon. How do those work? What do diodes do there?
Remember, AC current, it keeps changing direction, like a pendulum swinging back and forth.
Right. Positive, negative, positive, negative.
Now, rectifier circuit uses diodes to rectify that. It converts that AC into DC.
So the diode only allows current to flow during the positive swing of the AC wave and blocks it during the negative swing.
Exactly. It's like the diode's chopping off half of the AC wave, letting only the positive pulses through. The output isn't alternating anymore. It's pulsating DC, current flowing in only one direction, although not as smoothly as from a battery.
But hey, it's a start, right? That's how we get from AC from our wall outlets to the DC that powers our gadgets.
Exactly. And then we can refine that pulsating DC using other components. Speaking of which, we've also got sources on capacitors. How do those fit into the picture, even if our star today is the diode?
They're like the supporting actors, right? But still important to the plot.
Definitely. Remember, capacitors store electrical energy, so they can work with diodes to smooth out that pulsating DC.
So after the diode lets a pulse through, the capacitor charges up. Then when the diode blocks the current, the capacitor can release that stored energy, filling in the gaps.
Precisely. It's like a reservoir, smoothing out the flow, making it more continuous.
A tag team. The diode directs the flow and the capacitor smooths it out. Teamwork makes the dream work, right?
Exactly. And let's not forget transformers, mentioned in those AC sources, right? They can easily change AC voltages, something you can't do with DC. So typically you'd use a transformer to adjust the AC voltage, then rectify it with diodes, and then smooth it with capacitors. It's a multi-step process.
And it all starts with this humble little PN junction diode, just directing traffic one way only. It's kind of mind-blowing to think that something so small, so seemingly simple, is so essential to our tech-filled world.
It is. Think about it. Smartphones, laptops, TVs, even your kitchen appliances, most of them run on DC. And chances are there's a PN junction diode inside each one, quietly converting AC to DC.
And it's not just about power supplies, right? We've got LEDs. Those are light-emitting diodes that actually emit light when current flows through them.
Absolutely. They're a special kind of diode, but a diode nonetheless. And then there are Zener diodes for voltage regulation, photodiodes for light sensing. The list goes on and on.
So, by understanding the PN junction diode, we're really understanding a fundamental piece of how electronics work, how they control electricity, even if we never see these tiny components ourselves.
Absolutely. And here's a thought for you listeners. We've explored a single PN junction, but imagine the possibilities when you combine many of them. It's like, well, it's like using simple bricks to build complex structures. It's the foundation for the amazing things electronics can do.
Yeah, that's a pretty amazing thought. So let's wrap this up. Today's deep dive, we've explored, let's call it chapter 20 territory, the PN junction diode, that one-way valve for electricity. It's made by joining N-type and P-type semiconductors, creating that depletion region barrier. And it's got this neat trick. Forward bias, current flows, reverse bias, current's blocked.
And this simple behavior, it's the backbone of countless devices. Power supplies, LEDs, sensors. It's a basic concept with a huge impact on our tech-driven world.
So folks, next time you grab your phone, your laptop, anything electronic, take a moment to appreciate that little diode working behind the scenes making the magic happen. And hey, maybe this deep dive has sparked some curiosity. Maybe you want to explore further. Check out some rectifier circuits online, see how they work. You might be surprised at how much you can learn from this one tiny component.
How do those fit into the picture, even if our star today is the diode?
They're like the supporting actors, right? But still important.